Okay, let's begin. We're going to finish up limits and continuity. We only really have to talk about continuity at this point, and then we will move on. Pretty much everyone except right now has received your report card, so it sort of shows you what grades I have for you, so if you notice there's a mistake, you can come talk to me and we'll fix it. In general, how bonuses work, bonuses carry over to things of the same category, right? So if you get 100 on your test, and in addition you get some of the bonus problems, right? Those bonus problems, I can take them and add it to another test, right? I can't add it to a quiz or the final, only to other tests, right? Bonus on quizzes, I can add to other quizzes if you get extra, right? That's how it works.
You said that some things were already dropped. Are you just dropping the worst?
It just drops the worst grade automatically.
Every time you update.
Yeah, so once it updates, it's going to recheck and it's going to drop the worst too.
Oh, so something that's already dropped might then get...
Might then come back, right? So, so the program does the drops for me automatically. So it will automatically just search through all your grades, drop the 2 worst homeworks, drop the 2 worst quiz grades, and so on and so forth.
Who wrote the program?
Huh? I don't know. It's this company called Jupiter Grades that started. I have nothing to do with it. I just know it's a service that I subscribe to. It's like $50 a year, and I get to send these reports out.
That was my question.
So we're going to continue with limits and continuity. Pretty much all that's left to talk about is continuity. Which is the name of your computer.
That's where it's from, actually.
The definition is actually pretty similar to the one you did back in Calc 1. It's where the limit is equal to the value of the function. So we say f of xy is continuous at a point a comma b. Right, this is talking about continuity at a point if the limit as xy approaches ab of xy is actually equal to the function evaluated at the point. Right? You won't always be able to evaluate the function at the point, but in the case where you can, and it coincides with the limit as you approach that point, you say the function is continuous. Right? So a good way to see this back in 2D, you remember this was sort of like the idea where you might have a gap, right? So it's possible that you have the limit existing, but the y value that you're getting close to is not the actual y value that it's there. So it actually means there's actually a gap, right? So it's not continuous. You have to actually lift your pencil off the page, fill in this gap, and then come back and continue, right? So, and of course there are other cases. So that's the case where the limit can exist, but it's not continuous. And there are cases where it's not continuous because obviously the limit does not exist, which is, I showed an example of that last time, right? So we know something is continuous if the limit exists and it coincides with the value of the function at that point. And we say a function is continuous if it's continuous at all points in its domain, and a similar definition holds here. We say fxy is continuous on a set P if it is continuous at every point in right? So if you call a function continuous, it means it's continuous at all points on its domain. So those are some definitions. They're pretty familiar to the old ones, so we're just putting it in a different context here. Let's talk about polynomials and rational functions for a second. We will mostly Anyone knows what a polynomial looks like?
So with the form C x to the
Multivariable polynomial. In two variables, say.
A squared plus by squared plus cxy plus dx.
Right, sure, things like that. So it's this is a sum of terms having the form x to the n, y to the n. Right? So you have a bunch of terms that looks like this and you add them all together, where c is a constant and n and m are non-negative integers. All right, so example. I wrote down a nice one, but the one you had was fine. See something like 5x squared y plus 2x minus 3y plus 7 is a polynomial. Right, so in single variables, your only variable is x, so it looks like a n x to the n plus a n minus 1 x to the n minus 1, blah, blah, blah. But here you can actually mix the x and y's, and as long as they have integer powers that are 0 or bigger, you call it a polynomial. Anyone knows what a rational function is?
the ratio of two polynomials.
Right. This is the ratio of two polynomials. So, example, x, y equals, as far as continuity and and where they're defined go, what's the difference between polynomials and rational functions?
Polynomials are always integers all throughout their domain. Rational functions aren't necessarily so.
Their domain. Right, which means that always happens for a polynomial, which means to evaluate the limit for a polynomial, you just plug in the point that you're approaching. It will always just work out. Rational functions are continuous where? On their domain, but describe their domain.
Well, if you have, for example, in the one you wrote on the board, if 2y is equal to x squared, then that's not in the domain. Or I'm sorry, if
2y is equal to minus x squared.
yeah, that's what I meant.
Right. So
If
it's
you
where
divide
the
by 0.
denominator is not 0. Alright, so you have to sort of shy away from such points. So therefore, we can do a couple examples of limits. I believe I showed an example of this the last time, but it's worth showing again, I guess. What did I put? want to find that limit. I believe the last example I gave you was a rational function that we plugged in the numbers into. Here we're plugging into a polynomial, and you can never fear, you can always just plug in the numbers that as they present themselves. So here it says x goes to 1, y goes to 2, you literally plug those numbers in. So it's just 2 times 1, 2 squared, minus 3 times 1 squared, times 2, plus 2. That's 8 minus 6 plus 2. Okay, so polynomials are nice, you can just plug them in. Rational functions are not so nice, especially if your limit is approaching a point where your denominator is 0. Then things are kind of weird. And let's do a couple examples of that. Let's play where's the function continuous.
Are we preparing for the Olympics?
Okay, where's the function continuous?
All points except the origin.
Here, f is continuous where at all points such that x squared plus y squared is not equal to 0. i.e., it's continuous on the set of all x, y such that x, y is not the origin. Okay, so you just set the denominator equal to 0, and wherever that happens, that's not in the domain. That's how you deal with rational functions. What about part B, though? It starts out similarly enough. It's the same function when you're not at the origin, but then at the origin I define it to be something else. Where is that continuous?
The first one?
Are all points?
Everywhere. Why?
Well, all points, because it has a point at 0.
Because what?
Well, it has the point at the,
But you can't have 0 in the denominator because once you have 0 there, it's undefined. But could you use L'Hopital's rule?
Technically, isn't it a piecewise function?
It is a piecewise function.
So, I mean, if there's there still could be a discontinuity.
There could be. How do we know if there is or not?
We would have to check. as you approach left and right.
The point where it meets. Clearly, if we're not at the origin, there's no problem, right? We would divide by 0, everything's hunky-dory. That's fine. The origin is really the problem. So we can say clearly f is continuous if we're not at the origin, right? Now, assume xy is equal to 0, 0. How do I know if f is continuous or not? How do I check continuity at the origin?
Well, you need to find the limit.
The limit.
0.
Check that the limit as you approach the origin of f of xy is actually equal to f of 0, 0, which is defined here to be 0, right? So here I said at the origin I define my function to be 0, right? If I'm not at the origin, I'm that. So what I'm going to do is I'm going to take a limit approaching the origin, and I should get the same definition at the origin, which is 0. And is that the definition that we got? Since equals 0, we actually did this in last class. Right, we used the squeeze theorem to prove that the limit of this was indeed 0. Right? So the limit is 0, which is equal to f of 0, 0. Therefore, f of xy is continuous at the origin, right? Because the limit coincides with the value of the function. Turns out this is a discontinuity that we had here, but it was a removable one. There was literally only just a point that was removed. Now I filled it in with the right value. And so now I get that f of xy is continuous everywhere. Because of how I fill this in. If I had filled this in with any number other than 0, it would still be discontinuous at the origin, right? That should be something you should be aware of, right? Because then the limit would be something other than what I defined it to be. So that's an important distinction. And problems like this come up on finals all the time. So it's something that they do expect you to know, right? So you should be able to examine a function and know where nothing's going to happen, right? And then everything's great. And then you should be able to pick out the points where bad things happen and then do this check, right? The limit coincides with the evaluation of the function. Everything's good again. You're continuous. And you just move on. If this does not happen, then you say, oh, it's discontinuous there. Right? It's continuous everywhere else. Other properties of continuous functions. Continuity has certain properties. Assume f of x, y, and g of x, y are continuous. Then f plus g is continuous. Right? The sum of two continuous functions is again continuous. If you subtract them, it's also again continuous. F times g is not. Subtract g is continuous. Take f divided by g is continuous where g is not equal to 0. Right? And of course, if you take a constant times a continuous function, it's continuous. And so on and so forth, right? You can combine continuous functions and get another continuous functions unless you do something like, division where, 0 becomes a problem. So continuous functions, they play well together. That's one thing you should know. So we talked about polynomials and rational functions, but you should be able to figure them out for functions that are not of this type. Oh, composition is also continuous. F of G. Like if I give you such a function, right? It's not a polynomial, it's not a rational function either. It's a trig function where you plug the rational function into the argument. Where is this continuous?
Y is not 0.
Describe that region to me. In 3D space, what would that be describing? Tell me all the points in three-dimensional space that this will be continuous.
Everything.
Except the origin.
Except the XZ.
Except the XZ plane.
Yeah.
Continuous everywhere but the XZ plane. Right. Again, why? Because this is continuous when y is not 0, and then you compose it with sine, which is also a continuous function. So as long as this guy behaves, overall you'll have something continuous. Right? And y is not 0 means you're not on the xz plane.
So if y goes to 0, you are
On the
that's
XZ
the
plane.
only time you're on the xz plane is when y is 0?
Yes.
Okay.
Just like in 2D, the only time y is 0 is when you're on the x-axis. The only time x is 0 is when you're on the y-axis. Can't have it any other way. Where did I put that? End note to this section. Yeah. It turns out to go from a one-dimensional function to a two-dimensional function was actually sort of a big jump, but to go from 2 to 3 or 3 to 4 or 5, it's actually not that bad. Things, you pretty much extend the formulas and everything holds the same way. So instead of writing down 2 variables, now you write down 1. And you look at 3 components approaching something instead of 2. Right? Everything becomes easier. Once you enter the higher dimensions, things flow nicer. It's just 2 dimensions is very limiting. Yeah, but that's it for 11.2. The homework for that is due tomorrow. Should I start at 11.3?
No.
No.
What? We have like, what, 15 minutes?
Whoa.
It's the summer, we can't waste all that
You'll
time.
watch this one.
We're tired.
Okay, fine, go home, do the homework, relax.
Oh, okay.